Hi everyone, the next topic is Gauss Markov Theorem. So this theorem guarantees some good properties for least square estimator beta hat. We have studied beta hat. Beta hat is defined by minimizing sum of squared residuals. And how this estimator is justified? Gauss Markov theorem guarantees some good properties for beta hat. So the least square estimator beta hat has smallest variance among all linear unbiased estimators. A linear unbiased estimators means that the estimator satisfies this condition and this condition. So first condition means that this estimator is a linear combination of observations y1 to yn. And the second condition means that on average, this estimator is correct. So expectation of beta tilde is equal to beta. So if we have many data sets and we have several estimates, many estimates of beta tilde, on average, that approaches to beta. So as long as we assume beta tilde has these properties, beta hat is the best one among these. And here, also, I would like to explain the meaning of this smallest variance. If beta hat only have one component, the smallest variance is clear. So just variance is smaller than any other estimator. But if we have beta hat as a vector, the smallest variance is a little less clear. So for vector beta hat, the smallest variance means that this covariance matrix has this property. So beta hat has smaller covariance variance. That means variance of beta tilde minus variance of beta hat is positive definite. So variance of beta tilde can be variance of beta hat plus some positive definite matrix such as 1002, but we have never have matrix such as variance of beta hat plus -1 to 0 or -2 -3. We have never have these cases. So always this part should be positive definite matrix. So that guarantees any linear combination of beta hat, for example, beta naught hat plus 2 times beta 1 hat, that has smaller variance than beta tilde naught plus beta tilde 2 times beta tilde 1. So for any linear combination of estimates, the beta hat has better property. So next, proof. So proof also just uses some linear algebra and property of expectation and variance. So suppose that beta tilde is equal to zy, since beta tilde is a linear unbiased estimator. So z can be written as this way. So x transpose x inverse x transpose plus d. So first part is for beta hat. And the second part is difference between beta hat and beta tilde. So that's why we say D. So D is here P by N matrix. Then expectation of beta tilde should be beta. So we write down this and we just simplify it to derive some property on D. So beta tilde is zy, so this, and z is this matrix. And also y is equal to x beta plus epsilon. So we can get this. And epsilon, remember that the expectation of epsilon is 0. So 0 times something is always 0. So epsilon can be ignored from this equation since we take expectation. So we only have the other term. And first term x transpose x inverse x transpose x, that is just identity matrix. And so we get this. So first term, the identity matrix times beta is just beta. So second term, dx times beta should be 0. So what's this condition? Beta is actually p-dimensional vector, p by 1. And this dx is p by p matrix. So this should be 0 for any beta, any possible true beta. So that means the matrix dx should be 0 matrix. So to make beta tilde unbiased, this dx should be 0 matrix. So next we derive the variance of beta tilde. So beta tilde is zy. So variance of zy is in general z times variance of y times z prime. And here variance of y is equal to variance of epsilon, because y is equal to x beta plus epsilon, and x beta is not random. Non-random term doesn't matter for variance. So since this is equal to identity matrix times sigma square, just we interchange the position of this identity matrix and z, we get the sigma square first, then z times z prime. And z is this matrix, z prime is this. So we transpose this because we have 2 terms, so we get this. Then, okay, if we expand, we have 4 terms, and first term times first term, so x transpose x and x transpose x inverse cancel, so that becomes x transpose x inverse. And d times d prime, so that just remains. Other term, this appears because of the condition dx is equal to 0 matrix. You can see d times x and also x transpose times d transpose. So this disappear. So finally, we get this. And dd prime, this is always positive matrix for any matrix D. So actually, we have proved that the variance of beta hat is always smaller than the variance of beta tilde unless D is equal to 0. So this is the proof for Gauss Markov theorem.